The exploration and eventual landing onto the Martian surface has long been imagined by scientists and explorers alike. However, in order to make this an actual reality, a lot of work needs to be done in improving certain technologies to allow humans to live on the surface of Mars. For example, how would cargo be transported around the surface? Our job as engineers was to create a fully autonomous vehicle called a macro that would be able to transport cargo supplies to various drop-off locations around the Martian surface. The macro would be successful if it were able to precisely navigate to specific drop-off locations, either 1, 2, or 3 in our case, and drop off a specific type of cargo, that being a cylinder, a cube, or a cone. 2, to recognize and handle the hazards on the Martian surface, hazards including sloped terrain, half-destroyed path. 3, to deliver mission hardware timely. For example, they needed to be delivered within a certain time frame. And finally, to transport cargo from location to location without dropping or tipping, because otherwise the cargo would be lost and the human population would not be all right. However, these were only the preliminary tasks for us to handle, as the real challenge was realizing how to integrate the code and building in order to accomplish the individual tasks of the macro. In order to successfully navigate such an extensive project, we first had to iron out the project management aspects.
We started out by stating specific goals that we had in mind and that we would keep looping back to throughout our process. Those goals were to line follow, to go around obstacles, offload cargo, and to be able to use the magnetic sensors to go to the correct drop-off sites. If we could follow all of those, and if we could successfully implement each into our design process, then we would create a very successful macro robot. We started out by brainstorming what we needed to do to fulfill those goals. We looked at prior art, and the most successful macro, debatably, was the Mars rover designed by NASA. Thus, we looked over it for inspiration. The Mars rover accomplishes its goal of avoiding obstacles by having camera sensors built into the body, which is elevated in the middle of the rover, so it can move around, which we could implement into our design using the ultrasonic sensor. The rover has ground-penetrating sensors to discover minerals and other chemical compositions underground, which is also similar to our project, as there will be underground markers for where the offloading locations are located. The power supply is in the back in order to ensure the rover is evenly distributed and doesn't fall over. We also used worst case possible to basically include all the elements of a non-working macro robot in order to try to gear our process to something that could make sense. We talked about something that couldn't follow the line, something that couldn't offload cargo, and many more.
We made a functional block diagram with the main components such as cargo, drivetrain, and power and showed how they interact. We made a work breakdown structure identifying the main components of the macro, with those being drivetrain, cargo bay, cargo offloader, and control system, and gave a brief timeline of the process to design and optimize them, finishing with the final product.
We also used need-finding charts for each subcomponent so that we could maximize our success. For the customer needs for the drivetrain, we talked about how we needed it to move forward and backward at a desired speed, to rotate the robot counterclockwise and clockwise at the desired angular speed, to accelerate and brake when needed, and to overcome even terrain. Our target values were to go about 20 centimeters per second forward and backwards, to be able to rotate at about 6 degrees a second, to have a acceleration and deceleration speed of about 5 centimeters, and to overcome about a 20-degree incline. For the cargo bay, we decided we needed a large cargo bed to carry up to 3 items, and we needed to hold it in a stable position so it would not fall on the track. For the cargo offloader, we desired a 100% success rate on releasing our cargo top side up, and we needed to quickly drop off the cargo to maximize the time that we could run around the track, and that time was about 3 seconds to complete the process. For the control system, we needed it to be all autonomous. We needed to use sensors to inform navigation decisions as opposed to user-defined inputs. We needed to use sensors to inform actuator movements in the motors. We needed space to mount the control board onto the body of our macro design. We needed to mount the power source around the same area, and the battery supplied power throughout the whole test. We created a Gantt chart to help stay on schedule throughout the entire process. We wanted to start the code very early to make sure that we could build the robot around what we tried to do. We wanted to design the drivetrain, test it, design the cargo bay on top, test it, and make sure that it works. We wanted to design the cargo offloader, and by that point, we would have everything working.
The two biggest factors while considering the design of the macro were the driving and unloading mechanisms. For the driving mechanism, we considered four-wheel drive, two-wheel drive, and tank drive. Four-wheel drive would provide greater traction and control. However, it seemed too complicated for its benefits to outweigh its difficulty to design and code. With two-wheel drive, we would have the same amount of stability with four wheels, but possible unwanted friction. With three wheels, we would have less friction, but possible instability in the macro. Tank drive would provide the most stability and still have control. At first, we thought six wheels was the best, but after seeing unwanted friction happening, we eventually went to four wheels and then two-wheel tank drive. For our offloading mechanism, we considered a motorized wheel to push off the cargo, a wide ramp either behind the drivetrain or above the drivetrain, or a long ramp above the drivetrain. The motorized wheel idea seemed too likely to be inconsistent, and the wide ramp ideas seemed too cumbersome, so we worked with the long ramp idea. After starting to build the macro, our team was catastrophically hit with COVID-19. As seen on the figure, our group was separated for over 2 weeks, and 2 of us were sent to Purdue Village. Ashish had a pre-existing condition, but heroically willed his way through the virus. COVID-19 restricted our building and workflow. We worked online through video calls and could only have a single builder. Our full team reunited with a day left before the final demo. Before the redesign, the Raspberry Pi mount and the poorly made support of the ramp caused an uneven distribution of weight and problems with the drivetrain. Because we still had four-wheeled tank drive, the motor spun an axle which spun 2 wheels. In our redesign, we removed the back wheels to decrease friction and attached the motor directly to the wheel to eliminate possible error in the gears and axles. Additionally, we reconstructed the ramp for stability and proper support. The final ramp was set at a steeper angle than before as cargo fell more consistently upright with this design. The cargo will be set in place on the ramp and held by walls and a swiveling gate as seen in the pictures. When ready for drop-off, the gate would swivel open, causing gravity to pull down the cargo and land upright. As seen here, the gate would swivel upwards, wait until the cargo is dropped, and then return to its initial position. We attached 2 line sensors on the front of the macro, so a line was always detected and decisions to turn were made consistently. Line sensors were slightly in front of the wheels, so decisions could be made on time. The hall sensor was placed at the bottom of the macro, extremely close to the ground to detect the magnetic beacons. The hall sensor was in the middle of the macro because decisions to turn and drop off were not pressured by time and didn't need to happen immediately.
So for the software logic, starting with line following, the code works independently for each motor. If the line sensor is over the white, it'll tell the motor to go forward, and if it's over the black line, it'll tell the motor to go backwards. We had to adjust the power values to tune in the turning radius. If it was too low, then the macro wasn't able to turn at all. And if it was too high, then the macro was too finicky and wasn't really able to move forward. The older version of this code used a while loop that told a wheel to go backwards if it was over the black line. And this worked well. It allowed it to go a little bit more straight along the line. However, the kind of alternating motion that this new code has allows it to follow a dotted line, which is something that was essential to us. For the cargo drop-off, so first the code resets the encoder position so that wherever the motor is currently at is now the encoder position 0. And then it tells the motor to go to a certain degree position. We chose 180 degrees because this ensures that the arm is fully out of the way of the cargo and lets it slide out without hitting the arm. It's then held in the open position for 3 seconds. This gives plenty of time for the cargo to fall off and fully deploy and make sure that the arm doesn't hit the cargo on the way down. And then once those 3 seconds are up, the arm resets to the 0 position and is in the closed position. For beacon detection, we use an analog hall sensor. We chose the analog over the digital sensor because the analog allowed us to tune in the precision a little better because it gave us a larger range of values that we could work with. So what it first does is it reads the hall sensor value. I subtracted 1900 just so that the numbers would be smaller and it would be easier for me to see if there was a difference in readings. If the value is less than a preset threshold, a threshold that we determined by testing, then it says that the beacon is detected. If we want to count the beacons, we tell the robot to sleep for 2 seconds after the first detection to avoid it detecting the same beacon multiple times. So the integration of this code, bringing it all together, we did a little bit of pseudocode. We knew the order we wanted it to be in. If you look on the image on the slide, you'll see that there's different sections there within the code. First, it line follows until the beacons are counted to the indicated drop site. This is a variable that you input. Say you want to go to drop site 2, you'd input the value of 2 for that variable, and then it would count the number of beacons. So once it navigates to the drop site by line following and counting the beacons, then you have to deploy the cargo. That's its own section of code, and then has to line follow back to the landing zone. And although this was only 4 steps, there was a lot of minor issues along the way. especially turning on to the drop site, because our typical line following code was not super reliable for choosing the right path, so we had to do specialized code for that. Before even integrating everything, we had the individual segments of code. For example, the independent line following, cargo drop-off, beacon detection. So all we really had to do was just stitch it together using logic and control structures. And finally, for the speed test, first we calculated the angular displacement, like how many radians the motor needed to turn to get the desired linear distance. And then we calculated the angular velocity that the motor had to go at to get the desired linear speed. Once these values were calculated, we set the motor DPS, the degrees per second, and what this function does is it takes into account the load. The reason we didn't do set motor power is because this doesn't take into account the load on the motor. So using set motor DPS allowed us to set a very accurate angular velocity, and by reading the encoder, similar to how we did the gate for the cargo drop-off, we were able to go a very accurate distance.
Next, we need to consider the pros and cons of our prototype. The first pro being our ramp, as our design was large enough to hold all the different types of cargo and could deliver them without tipping each time they were offloaded. For instance, in a trial of dropping off cargo 20 times, the cylinder was offloaded straight 20 out of 20, the cone 16 out of 20, and the rectangular prism 19 out of 20 times. Therefore, very precise. Along with the cargo offloading time being pretty low at 4.69 seconds. The next positive design feature of a robot was attaching the motors directly to the wheels. Compared to our previous design, this delivered more power and was also 100% better in the line following tests when it came to the dotted line and also the dashed line. Finally, we were able to successfully implement a consistent way to measure speed and achieve a specific velocity. As shown in the graph measuring centimeters per second, with our target goal being 20 centimeters per second, in 20 trials, we were within 0.8 centimeters per second each time, and the slope of our linear regression was nearly zero, showing just how consistent the measured speed was. Next, we need to consider the cons. Our first con being that our back wheels, which were bent Lego pieces, were not successful in getting over the first obstacle and had a significant amount of friction on the gym floor compared to the practice area, which inhibited our ability to turn. When tested on the practice terrain, out of 20 trials, on the most aggressive turn, we had a minimum turning radius of 3 plus or minus 0.2 inches. However, this was not the case during the actual test. Next, we ran into a problem with our line finding code, because it did not consistently have the ability to turn at the magnetic beacons to go then drop off the cargo. Out of 20 trials, it only went down the right path 5 times, deciding rather to go straight, which was something that we should have improved on. Finally, our drive deck could have used some improvement, since it was too close to the ground and at one point had our Hall sensor get caught. Additionally, it only had a 60% success rate of identifying both beacons and offloading the cargo. In conclusion, our physical and software was flawed, as the Hall sensor and backside support systems could not get over the obstacle and made it hard to turn, and in our software, we were not able to accurately identify both beacons and offload the cargo consistently. Therefore, in order to improve our macro's performance, a couple of things needed to happen. The first being the back wheels needed to be replaced by actual wheels instead of curved Lego pieces, which not only would remedy our problem of not being able to get over the obstacle, but also would help with making it around the tight turns in the track. The specific way to change this would be to attach wheels that could swivel in the back, which would then lift the macro further off the ground and allow for tighter turning. We also need to make the drive deck higher off the ground, which starts with making actual back wheels, but aside from that, we would then attach more supports between the ramp and the deck, and also horizontally between the components, making up the drive deck and improving its stability. Another thing we needed to improve is the code for the Hall sensor. This is because one of the worst parts of our robot was its inability to successfully identify the beacons and then trigger the offloading of the cargo. A change that would make this better would be to find an increased range of values using the analog Hall sensor, and we should have tested more to figure out a wider range of those values that would then signal the Pi that the macro was over the magnetic beacon. Finally, one of the most important improvements we should have made was in the line finding code. Once the first magnetic beacon was identified, the macro needed to be able to turn to the right consistently, rather than our pitiful 5 out of 20 success rate. The way to accomplish this would be to first improve the identification of the beacons, and then to implement a while loop that reads for the beacon and turns the macro by making the right side stop moving and only the left one move forward. That way, you could tell the macro how many beacons to go before it needed to use that code, and then drop off the cargo, which would be overall much more successful. Therefore, while there might have been a myriad of issues that needed to be fixed for the true success of our macro, in theory and in a practice, we all had the necessary elements to run a successful cargo mission on the Martian surface.